camera.
Yeah, but those cameras were really old and slow.
Even at that time, no one was able to do it, right?
Yeah. Okay.
Oh no! Actually, his hand.
Oh, hey,
was
both of you
faster
stand
than
there.
the
Both of you
bullet.
stand on that side. You too. Okay. Right.
It's on.
We forgot our friend.
Your imaginary friend. It's in. It's all recorded.
Alright, this is ME450 Senior Design. We're Team 24. Our project is a mobile bioimpedance measurement system. Our sponsor is Dr. Kevin Ward. He's a professor of emergency medicine. So our project goal is to create a wearable and wireless bioimpedance sensor that measures your body's bioimpedance signal. And to do that, we inject a current into the body at a frequency of 10 to 100 kilohertz and wirelessly transmit the signal to a receiving computer. So the benefits of having a mobile solution over a stationary system is that patients will be able to be discharged from the hospital sooner, and physicians will be able to monitor their health remotely from a home setting. So what is bioimpedance science? Bioimpedance generally is the response of a living organism to an externally applied alternating electric current, in this case the human response to an applied current. And from the human bioimpedance signal, we can gather all of the standard patient vital signs, including central venous pressure, heart rate, respiratory rate, heart stroke, cardiac output, and detection of edema. So the pictured here is a commercially available bioimpedance sensing system made by Biopack Systems. As you can see, it's very large, bulky, hard to transport, and for this reason, it can only be used in a hospital or laboratory setting. So our goal is to create a mobile version of this system. Pictured here is the model of bioimpedance in humans. Our ENT represents the resistance of intracellular fluid. Our EXT is the resistance of extracellular fluid. And C represents the capacitance of cell membranes. And it's this capacitance that makes bioimpedance an impedance rather than simply a resistance. Now Tim is going to talk about our sensor design.
So this picture shows the first mobile solution for health monitoring using bioimpedance science that we designed and implemented. This table shows engineering specifications that we targeted as well as final values. The size of this device is 3.5 by 3.5 by 5 inches, and the weight is 625 grams. This figure shows the system operation of the system. As Jason mentioned, we need alternating current, but it's also supposed to be mobile. So we use batteries and oscillator that converts direct voltage of battery into alternating voltage. Then current source converts alternating voltage into alternating current, which has constant amplitude. Which also sends the current through these two electrodes that are on the sides. Then we compare this voltage difference of area of interest in two inside electrodes and clean the data using low-pass filter. Then after the data is cleaned up and there is no noise, the data is transmitted using XB to the computer in order to monitor the vital signs. So we tested the wireless range, and it was from 10 to 100 meters. Depends on the environment we tested, and also we estimated battery life to be 12 hours. Frequency we're sending through the person is at 40 kilohertz in order to identify the bioimpedance. And most important is the safety issues, of course. So the current we're sending is 380 millivolts peak to peak, which is much less than this threshold of sensation of 1 milliamp. And now Ali is going to continue about material selection.
So for the dry electrode material selection, we started with 5 options of metals according to our sponsors' requirements of having non-disposable electrodes. So we started with those 5 options and compared them according to some criteria we have shown in this diagram. And the platinum and gold metals were the best. However, they are very expensive, so we decided to go with the stainless steel for the low cost and for the low contact impedance for the small diameters we're using. And then we had 3 different electrodes for our sensor system in order to show to the customers or the sponsor. And then for the wireless communication, we started with the Zigbee wireless radio after comparing it to other Bluetooth and Wi-Fi options. And it turned out to be the best one because of the high range it has, which we mentioned, of about 100 meters. And then it has very low power consumption, and also it's very small in size. And so as for our results and how we compared it to the commercially used BioPack system, we showed both digital and analog on oscilloscope and computer results, and we have proven the low consumption, like Tim said, about estimated of 12 hours of continuous use, and also the wireless communication was validated by trying it between hallways and in the labs. We also have some future work because this device can also be smaller than this. So the first thing we have is making this circuit as a printed circuit board. That will definitely make it a lot smaller, with having the Arduino and the Zigbee radio on it as a chip in order to do the same functions. And also we have the metal of the or the material of the electrode. We can use platinum or gold if we have a better budget. And then thank you very much, and thank you everyone that helped us.
Yeah, we'd like to thank Professor Shi, Professor Gilchrist, Professor Taub, Dr. Tiva, and of course our sponsor, Dr. Ward. Thank you.
Thank you.
I forgot the batteries. That's the last thing.
The batteries.
Like future work, so we have time.
Oh yeah, whatever.